things. So we're going to talk about the science behind fire. Why do we need to know?
Firefighter.
Okay, because we're firefighters.
Know how to take it out,
What's that?
know how to put it out.
Okay, to know how to put it out.
I was gonna react with what we're doing. So like
Yeah.
operation plans.
Sure, we want to be able to know what's happening and predict what's going to happen and how our actions will affect it, what we can do to change the outcome. A few things that we're gonna go through. I'm gonna try and breeze through some of the PowerPoint stuff. I've got some videos. I'm gonna do a better job of explaining some of the science behind fire. We'll start with this one.
These mushrooms make you feel better. Like,
Hey everyone, thanks for tuning in to Test Tube Plus today. I'm Trace, and this is episode 1 of 5 in our new series on fire. Like, you know, fire, flames and stuff. Subscribe so you get all of the episodes in this series. Trust me, it's going to be really great. You can also check us out over on iTunes if you want to listen to the series. It comes as one podcast. It's easy to find. But this week, we're going to talk about what fire is exactly. Like, think about it for a minute. Do you know what fire is? What makes the flames? What are they made of? And when did fire become a possibility here on Earth? And when did we harness it? Also, we're going to talk about burns and cooking and firefighting science, because there's this whole branch of science related to fire science. We're going to talk about all sorts of stuff, even fire not on this planet. It's going to be really, really cool. But first, let's define that big question. What is fire? We've all been around fire. We've either made fire, we've seen fire, we've lit matches, all sorts of different things. Basically, fire is a chemical reaction that needs 3 things. They're referred to as the fire triangle. Oxygen, that stuff around you, you breathe it in all the time. There are other oxidizers that can produce fire as well, but that's the big one, you know, nitrites, chlorates, nitrates. The most common though, oxygen. It also needs fuel, which is like solid wood or gasoline or any number of other combustibles, methane, so on and so forth. The third is heat, and it might seem kind of counterintuitive that heat would be part of the triangle, but you need heat to start fire. Yes, it generates more heat as it goes, but the heat is part of the fire triangle. 3 things you need to start fire. Heat could be from the friction, like when you strike a match, or it could be from an electrical spark or from a chemical reaction that releases energy. There's also another segment which people add that could be the fire tetrahedron. I know we just got to triangle and we're upping the game already, but stick with us. The 4th element is redox, or a rapid oxidation, a chemical chain reaction, essentially. The oxidation is the interaction between oxygen molecules and something else. So one of the things loses electrons. Think iron, right? When iron is left out into the environment, it will rust. That is oxidation. It's exposure to oxygen. And it loses electrons to the oxygen in the air. So when heat is added to fuel and oxygen, eventually the fuel source will lose electrons and oxygen will gain them. This molecular transfer creates heat and or light, which in turn will then create fire. Now, the reason some things catch fire and metal just would rust is because the oxidation has to be rapid. If the heat made by this process can't be released faster than it's being created, you know, can't get dissipated faster than it's being built up behind it, then you have rapid combustion, and the rapid combustion is what eventually creates fire and flame. Now, this is still just kind of how we make fire, right? As the fuel heats up, let's say the wood, for example, like in a campfire, it gives off a gas. Sometimes you can hear it when you're sitting next to the fire, a hissing sound. And this is called pyrolysis. The gas escaping is actually what's being lit on fire, not so much the actual wood. The gas is what makes the flame. The pyrolyzation process takes the oxygen out of the wood, and what is left
I guess I can't do 2 things at once here.
is mostly carbon. And that's what you see when you are done burning a campfire. All the little chunks are charcoal, mostly carbon, the ash byproduct of wood, the impurities that cannot burn, calcium, potassium, those sort of things. Now that the fire is going though, it gives off heat, and heat is what helps the fire continue to burn, to pull more oxygen out of the wood, to get more fuel and get more oxygen underneath it as the heat cycles the air around it. It basically ensures that the fuel remains at the ignition temperature, it's hot enough to keep burning, and the flames produce more gas, and so on and so forth. You might notice that flames always seem to go up. Flames being hot means they're less dense than the air around them, right? They will naturally have more energy and they'll move upwards into trying to cool off and get a lower pressure. And then colder air comes in underneath and heats up, and you end up with this cycle. It's also why fire spreads upward. It also spreads by heating things up around it sometimes. So if you have a really big campfire, sometimes things on the ground nearby can catch fire as well. That's why you have to clear the area before you make a fire. Now, if you want to put these fires out, all you gotta do is break that triangle or break the tetrahedron. You get rid of the fuel. That's what firefighters do by cutting lines or blowing up buildings in the way of a massive fire. You can cool the fuel down by throwing water on your campfire, something like that. You can take away the oxygen, so putting a jar over a candle would do that. Or you can break down the chemical reaction. So if you use a fire extinguisher that has CO2 in it, you're snuffing out the fire by removing the chemical reaction from the area. What fire is this chemical reaction, this exothermic reaction. It's releasing heat into the air. And that heat in turn creates more fire. So now that we know what fire is, and we know all this stuff about the chemical reaction itself, where did this come from? Like, how did we learn to harness it and use it for our own purposes? And how did we learn to take this chemical reaction? On top of that, hey everyone, thanks for tuning in to Test Tube.
Figure out how to get us.
Maybe I can't, well, can't drug.
There we go. Okay. Now we know that this is a little bit shorter.
In the mid-1800s, Michael Faraday gave a series of Christmas lectures for kids at the Royal Institution in
This is the Ergo Smart Base from Tempur-Pedic, and it responds to snoring, so you don't have to.
mid-1800s, Michael Faraday gave
Sorry, guys. Let me get this lowered here for you.
The Ergo Smart Base from Tempur-Pedic automatically responds to snoring, so no more hiding under your pillow, because this system actually detects snoring, then adjusts to help reduce it. During our Black Friday event, save up to $500.
Technical difficulties. Sorry.
In this video,
The Tempur-Pedic Adapt mattress was designed to help make aches and pains a thing of the past, because only Tempur material eases your pressure points in a way no other mattress can. During our Black Friday event, save up to $500 on select adjustable mattress sets.
mid-1800s, Michael Faraday gave a series of Christmas lectures for kids at the Royal Institution in London. And one of his favorite subjects to talk about was fire. Faraday was particularly interested in candles because inside their delicate flames, they hold some amazing lessons on how fire really works. Now, you might have seen fire described like this in chemistry class, but the chemical formula doesn't explain what fire is any more than a recipe explains what chocolate chip cookies taste like. The first thing we notice about a candle flame is all those colors. A lot of things glow because of black body radiation. We talked about in our video about the color of the universe. But down at the bottom of the flame, it's hotter, so it glows blue. And in the middle, it's a little cooler, so it glows yellowish, orangish. Inside of that flame, there can be hundreds of chemical reactions taking place. The oxygen in the air and the carbon and hydrogen in the candle don't do anything on their own. It takes a little outside heat to get things started. Solid fuel is vaporized by the heat and ripped into smaller chunks. This is called pyrolysis. You can't have a flame without it. You can sometimes see a dark cone around the wick where there's no fire. Or vaporized wax is coming off the candle, but it hasn't started to burn yet. The hydrocarbons and oxygen in the air slam into each other, and their atoms begin to rearrange. Sometimes electrons in those atoms get into an excited state. When they come back down again, they give off light. That's why the bottom of the flame glows blue. Not all the carbon in the candle gets converted to CO2, so leftover carbon atoms come together and form tiny particles of soot, which heat up and glow orange and yellow like the hot coals under a grill. This glowing soot is where most of a candle's light comes from. Eventually, at the tip of the flame, all the soot is burned away, and we're left with only carbon dioxide and water floating off into the air. You can investigate all the different parts of a flame for yourself with just a cold piece of metal. Up here, we find water vapor. In the yellow part of the flame, soot. And down just next to the wick, we can even recover unburned wax. Flames look really cool too, they're almost. Wait, what was I talking about? Oh, right, shape. Gravity pulls cool, denser air down and makes hot air rise. And this buoyancy is what gives flames their familiar shape. But if you light a flame in 0G, say on the space station, it'll look very different. All the chemical and quantum reactions that make a flame glow can only happen where it meets the air. So even though they look like solid cones, candle flames are actually hollow. As long as there's fuel and oxygen, the flame will burn and burn. Why? It's not the molecular ripping apart that makes a flame hot. It's the formation of new molecules and new bonds is what creates heat. And that heat drives the chain reaction forward, vaporizing more fuel, slamming more molecules into one another, and making the fire burn on. Our species has been gathering around fire for thousands of years, telling stories, asking questions over a flickering flame. And that's part of what helped make us human in the first place. Stay curious.
All right, does that make sense? Sort of?
Whatever there is for you.
Dollars on select adjustable mattress sets.
It's at home, your holiday headquarters. And you're ready to slay the season and save on Christmas decor, trees, ornaments, and more.
I can't wait.
Get a skate.
I've been doing that,
Really?
yeah.
Control delete. Last name change.
Think about the best night's sleep you
Okay,
Best night's sleep.
yes, we never know about that. All right, so when we have a fire, have you guys thought about what a flame looks like? So you have your fuel. Now, what is fuel?
A combustible material.
So a lot of times when we say fuel, people are thinking of gasoline or liquid. And would be a fuel? Okay, so we have. I'll tell you like, this is the case. Is the flame here? Where is the flame? Right there, right? And why is that? Is this burning?
No, it's the gas.
It's the gas here. Okay, so we're gonna take a look at that here. You guys can come closer if you want. Okay, so what am I doing here? And how am I doing that? So what did I apply to the fuel? Heat, and okay, so then what happened there? What did the heat do? Okay,
They warmed it enough so that it could generate.
and so what was happening with those molecules? Right, and then we go into what we call pyrolysis. And did you guys understand what he was talking there? What is pyrolysis?
Solid material.
And so lysis means breaking down, and pyro can be fire or heat. So we're breaking down this fuel, which is the the wax there. And you can kind of see, and you see like the different colors and layers. Okay. Now, so it's not the actual wax here that's gonna be burning, it's the gases, as the heat's applied, it turns it into gases, right? And those gases are flammable. So like when we have, say wood in a house that's burning, it's not the actual wood, but the breakdown and the off gassing on those wood, on the wood, that is flammable. Okay, so I'm gonna blow this out and then I'm gonna apply heat to it. And what do you think is gonna happen? See that? Okay,
And it's down into the wick. From the.
yeah, but it goes down, and why is that?
Because the gases have been able to expand further because there's no more ignition, so the gases are expanding up into the space,
Okay.
which creates a sort of a chain back down to the wick that can ignite.
So if we had gas here that is readily ignitable, right? And so I applied the heat to it and that ignited. And so that's exactly right. So we know in a fire, and we'll talk about that more as we move on, but when we're in a fire, you've got, especially like that big smoke. That's smoke can burn, right? Because we have unburned byproducts, we've got gases that are flammable, and you put it, we say piloted ignition, if you put a heat source on it, it can ignite, right? Okay, should we try it again? Cool party tricks. Pretty cool, huh? Okay, so now, remember what he was saying, why does fire burn up?
The cold and cold air,
It's heating,
and then it heats up.
yeah. So it's, yeah, and it's going from fire goes from an area of high pressure to an area of low pressure. And that's why we see like it fills up the box, which would be like a room, and it's trying to get out. And so as soon as we have like an open window or door, it'll push out that way. Okay. Make sense? Okay, so what's the difference between fire and combustion? Gonna activate smoke detectors.
That would be the speed of oxidation.
Oh, no, that's a great point. Okay, so we have oxidation. What is an example of oxidation that doesn't produce a flame?
Rust.
Rust, okay, yeah. And so why doesn't that produce a flame? It's a slow process. In order for it to be combustion or produce fire, it has to be rapid.
Is it copper oxidation?
Yeah, there's several different things that will oxidize, and we think of oxygen is our only oxidizer. There's other ones, but because oxygen is in our air, that's most common in when we're talking about fire and combustion. Okay, so combustion is the actual action, and fire is like the result of that action. So if you look in your book at the definition, you guys can grab your seats. But if you turn to page 190. Okay, so read me the definition for combustion. Whoever's got it up first, you can start reading.
A chemical process of oxidation that occurs at a rate fast enough to produce heat and usually light in the form of either a glow or flame.
Okay, so read me the definition for fire.
A rapid oxidation process, which is a gas-phase chemical reaction resulting in the evolution of light and heat in varying intensities.
Okay, so those sound very similar, right? So just think of combustion is the verb and fire is the noun. All right, so what do we have to have for fire to occur? Heat, okay, fuel, oxygen. And there's one other thing that, so we got the fire triangle is fire, heat, and, I'm sorry, fuel, heat, and oxygen. And then what is the fourth thing that has to happen?
Chemical chain reaction.
The chemical chain reaction, okay, and so that's the fire tetraheated, that's what you want to say. Okay.
Sure was.
Yeah. Okay, so we talk about matter, what is matter?
A collection of like molecules that either that have, I mean, how detailed do you want it?
Anything that occupies space.
Yes. Okay, physical materials that occupy space and have mass. Okay, so matter can undergo physical or chemical changes. So a physical change, what would be an example of a physical change?
Podcast.
Okay, so what's happening there? So give me an example.
Okay, the transformation of a solid into a gas.
Okay, and so an easy one to think about is like water, right? So when water is ice, is it still water?
Yes.
Okay. If it has evaporated, is it still water?
Yeah.
Yeah, it's just in a different physical state. Okay, and so I'm going to pause right now because we're gonna do an experiment. Take me just a second to get set up for it. Hope I didn't stop the recording here.
It's still the same material in these pants, but they're dyed. So they're different colors, so it's a physical change. Well, they could also didn't have.
It might have a.
Yeah.
You know. What happens if you cut those up?
And then it'd still be its component parts.
It would be parts of your pants,
Yeah.
but it's so. But if you burn your pants, they're not gonna be your pants anymore. They're not gonna be seen. All right, we talked about oxidation. So slow oxidation would be like rusting. But rapid oxidation is what gives us our chemistry. Okay, now there's energy. There is lots of different types of energy, but when we talk about energy, there is potential energy, and then there's kinetic energy. Go ahead. Oh my heck, what's happening? Oh Lordy. Thank you. Sure, what's happening here.